Hey everybody, and welcome back to Linear Algebra Online. So today we're going to talk about kind of how we can do like span, linear independence, and just in general like linear combination problems with matrices. We're also going to do a few kind of unrelated but also just important transpose properties at the end that I want to make sure that you know for some stuff coming up. So to start off, though, I just want to do another one of these kind of partitioned matrix problems. So if I was given this big, messy matrix and I was asked to square it, the best way to do this is definitely just break it up into like easy chunks. So if you take that partition, okay, basically I'm going to view M as the 4x4 identity matrix. And then I'm just going to call that upper chunk like A. And then there's a zero matrix, a 4x4 one. And then I'm going to call that lower chunk B. And so if I do M squared, right, then I'm going to get I to the fourth. And then I'm going to get A plus AB. And then 0. And then B times B, or just B squared, like down there. So this is nice because it gives me like a lot of the answer already, like basically half of it. So I would have like 1, 0, 0. I was thinking if I want to write it all out, but I guess I will. And then you have a 0 matrix down here, a 4x4 one. So I've got all that part done, and then basically I just need to independently do A plus AB, and I need to do B squared, okay? So B squared, if you do it out, you basically at this point you just have to do that part out by hand, but you would get 4, 4, 0, 0, 0, 4, 0, 0, 0, 0, 9, 6, and then 0, 0, 0, 9. And then if you do A plus AB, also kind of annoying, but better than trying to do this whole thing out by hand. So you get 0, 0, 0, 4, 0, 0, 4, 1, and then 0, 3, 0, 0, and then 3, 1, 0, 0. And so then if you just go and put those chunks in, you would have M squared. So this is very common trick if like the matrix has some nice structure to it. It's definitely easier than trying to just do it out by like pure brute force. I mean, the absolute easiest thing is just go to a calculator, but sometimes actually even on like a programming side of things, you would need to like computationally matrix multiplication is really hard. And so there's times where it's much easier to actually tell the computer that the matrix has this structure, and this 2x2 matrix is much easier to compute, and then you just go and do something like this on the side and this on the side, and you can do those on a calculator, but then like you know that like this half is always going to stay that way based on how it was originally. So it's just a shortcut that honestly does come in handy even in problems where you have a computer, but you just have to kind of be smart and tell the computer how to do an easier problem, which like this is an easier problem. All right, so main thing I want to talk about today is what we kind of call matrix algebra. So it's really just like we're going to revisit a lot of the stuff we did with vectors, like span, linear independence, and linear combinations, but it turns out that you can do all this with just matrices, and it really shouldn't be that surprising because a matrix is really just built out of vectors. So what applies to vectors should apply to a matrix. It really isn't that surprising, hopefully. So first question here, I'm going to actually use these matrices for a few problems. So the question is this matrix a linear combination of A1, A2, and I2, like the 2x2 identity? And so basically, symbolic form, I'm saying, like, can you take some constant C1, multiply it by A1, add to that C2 times A2, add to that C3 times I2, and get B? That's like the question. And so the way that you can kind of like use your calculator to help you with this stuff is basically make a big matrix problem out of this one, and then you're going to use like RREF and analyze the output, and you can answer the question from there. So C1 times A1 would look like 0 C1 minus C1 0, and then plus C2 A2 would look like C2 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 C2. C3, it's a 2 I2 would look like just C3 on the diagonal. And then B is, we'll give it purple. Whoops, that was supposed to be an equal sign. 1 4 2 1. And so the idea here is, so now do this big matrix addition problem, and you can combine that into C2 plus C3, like in the first component, and then C1 plus C2 in the second, C2 minus C1 in the third, and then C2 plus C3 in the fourth. And like that thing needs to equal 1 4 2 1, right? So this is where we kind of are going to formulate a very big matrix. So from that one in white there, I basically want like a system to equal 1 4 2 1. Basically, I'm just peeling this off, okay, down and like kind of creating like a column vector out of it, 1 4 2 1. And I want that C2 plus C3 is equal to 1. So if I'm I'm switching it around, so like it's like C1, C2, C3, and then the vector or matrix. And so this needs to be creating like a first row right here. So what that's going to look like is like there's no C1, but then there's a C2 and there's a C3. And then this one, right, is like 1 C1, 1 C2, no C3. And that needs to equal 4, right? C1 plus C2 needs to equal 4. And you just keep doing that. You get negative 1, 1, 0, 0, 1, 1, 1. And so now you can just take RREF of this thing, and you get 1, 0, 0, 1, 0, 1, 0, 3, 0, 0, 1, negative 2, and then you just get a row of zeros. And then this is like how a lot of problems in linear algebra feel. You look at this result and you think about, well, what is that saying? A row of 0 means that there's actually infinite amount of solutions, right? And so I've got infinite solutions. So the question was, can you get B from a combination of these? And the answer is just yes. Technically, you can get an infinite amount of ways. There's like all sorts of ways to add, a linear combination of these things and get B. And even from here, you could then figure out how to do that if you wanted to. So, but yeah, you can do it, is the point. And the weird things here, I think, are just how I'm sort of going from this to this. So just one more time, what I did there is I basically took the matrix and I made them into like column vectors. So 1 4 2 1, 1 4 2 1. And then I'm just setting here what the conditions that need to work out are. So C2 plus C3 needed to be 1. So 0 C1 plus C2 plus C3 needs to be 1. Then 1 C1 plus C2 plus 0 C3 needed to be 4, and that's that row. And so it's just kind of like a reorientation of what this says. I've just made a system of equations from it. So if that previous problem is if B was in the span of these two, it might be a good, because you can get this from a linear combination of these, then it's kind of good also to answer the question, what does the span of this look like? So if we were going to do that, we can do the same thing where we peel, these matrices off kind of into a column vector. So 0, 1, negative 1, 0, and then 1, 1, 1, 1, and then I2, 1, 0, 0, 1. And I'm basically concerned with what does that linear combination in general look like, right? So I'm like making a matrix and augmenting it with something like W, X, Y, and Z. And I'm going to do like RREF. And if I do RREF, I just get 1, 0, 0, X minus Y over 2, 0, 1, 0, negative X over 2 minus 1 half Y plus W, and then 0, 0, 1, X plus Y over 2, and then 0, 0, 0, W minus Z, all right? And so when I look at this, the thing that like gives me some important stuff to work with, I guess, there's no like undefined things first up here, like in terms of any variables on the bottom. Like if you had X minus Y over W, then W can never be 0. So you would never get things like that start off 0 and then like 1, 2, 3 or something like that. So there's no issues like that. Everything here is defined. But this needs to, in order to span, right, you need this to make sense. And right now this is saying 0 equals W minus Z. So if you think about that last part, basically this row is saying if 0 needs to equal W minus Z, then W just equals Z, right? So that's the only condition I have whatsoever. So if I have like a general, W, X, Y, Z matrix, W, X, Y, Z, like that, I just figured out that the only thing that really matters is that like W is Z. So I have like Z, X, Y, Z. And so this is actually how we would say the span of these matrices up here. It's basically any general matrix where the diagonals match. And down here, I just say like this makes sense with our last problem because I asked is 1, 4, 2, 1 in the span of these. And since the ones match up, like on the diagonal, it is, right? But there's all sorts of matrices that are. Like if you do 2, pi, e, and 2, that's in the span. If you do, I'll just leave it at that. That's an element of the span of these matrices. Just leave it at that. So anything, and like you could then actually like figure it out. Like from here, you could like you have your W, X, Y, Z, and then you can kind of backtrack and see how to actually get it based on this instruction manual, sort of. So you can plug in your X, Y, and Z's, and then figure out what you need in terms of combinations of these matrices to get this matrix. That's the idea. So another important concept that we've talked about is linear independence and dependence. And for those problems, what we basically did was we set the vectors equal to 0, and then we saw basically whether or not the C's were 0. And if all the C's are equal to 0, then it's linearly independent. If there's, if that's not happening, then it's dependent. So basically, if we think about this problem with matrices, then we can just do the same kind of trick I've been doing where I make a matrix, like a big matrix, out of these kind of little ones. So that's my A1. This is my A2. My I2. And I want to know, I want to augment this with 0 and basically solve this thing. And if the only solution is the trivial solution, then they're independent. That's the idea. And if you do this, you get that. And so what this is saying is that, like, truly, C1 equals C2 equals C3 equals 0. It's the only way to do it. And so, yes, basically what we just saw is, yes, they are linearly independent because the only solution to this problem, C1A1 plus C2A2 plus C3I2 equaling the 0 matrix is the trivial solution. And that's our definition of independence. If there was some non-trivial solution, like if you got something here that wasn't just zeros, then you could do the whole dependence trick where you like write one of these, like maybe C1 in terms of the others. And then then you could like basically move this over and like now you have C1, like some combination of A1 depends on these other matrices. One thing I always struggle with in linear algebra is like saying vector or matrix or linear transformation. One thing you're hopefully seeing already, and you'll continue to see, is that all these are kind of synonymous. So when I look at a matrix, I can think of it as a column vector, but I can also think of a matrix as a linear transformation. So they're all kind of the same thing, and so sometimes like, I think of this as a vector, but sometimes I think of it as transformation, sometimes I think of it as a matrix. And so it's a little hard to kind of say these results sometimes because they kind of just apply to all sorts of different things. All right. So unrelated to that last stuff, I want to just do a little bit more with the transpose. So there's some important results here. And they're in the book, like actually this is them right here. And these are just like properties of the transpose, and some of these are very intuitive. I'm not even gonna like talk about like if you take the transpose of a transpose, you go back to the original matrix. This one's also pretty intuitive because like if you just like do it out with like a simple matrix, you can kind of sell yourself on it. Like K is a scalar here. So basically you can pull scalars out and like the matrix scale transposed is that scalar times the transpose. This one I actually already proved last video. These two I want to say something about. So this and this are very important kind of results. So I want to talk about those two. And the first thing I just want you to think about are like if you do AB transpose, I think that most people would assume it's one of two things, that it's either AT, BT, or BT, AT. And or maybe they're both the same, I guess. That's the other option, right? And the order doesn't matter. So this is like, there's a formal proof in the book, and you can read it. I don't really want to get into it because it's in the book, and I don't think I need to like go over it. It's fairly straightforward, but I think the intuition here is honestly more important. So let's say like A was m by n and B was n by r, let's say. So that multiplication works. If you do ATBT, right, then you would get you'd be doing A n by m matrix, right? This is A transpose, times a B R by N matrix, all right? And if you look at that, you should be confused because you can't do that matrix multiplication. This does not work. You need this to be the same size as this, and it's not. But if you do BT AT, all right, then what you're going to do is BT R by N times AT n by m, and this works, right? These two match, and so you're basically going to get some sort of BTAT matrix that is an R by m matrix. So this is actually the right way to do it, okay? And it's so famous it actually gets like a nickname. But AB transpose is actually the BT AT1, all right? And the term that this gets a lot of times is socks and shoes. And it kind of makes sense, okay? Basically, if you assign B as socks, right, and A as shoes, the idea here is, like, when you do this matrix multiplication, you always read it from the right, right? So you put your socks on first, then you put your shoes on. But if you're going to take them off, you actually take your shoes off first, right? And then you take your socks off, okay? And this kind of reverse pattern thing happens in math, oddly enough, in like a lot of places. And they kind of throw this term socks and shoes around whenever that stuff pops up. And transpose is one of those. And if you want to read the formal proof in the book, it's only a few lines. It's actually probably good for you to read it. I think it's like right at the end of section 3.2. But I think the intuition here is honestly the more important part. So think socks and shoes when you see this thing. Basically, socks go on, then shoes go on. And if you're going to take them off, then you take off your shoes first and then your socks. That's how you kind of peel it off, okay? So, I sort of already talked about this. The proof is in the book. I'm going to do that annoying math teacher thing that my professors used to do and drove me crazy, but I just don't have enough time. So I think it's actually, I just looked it up. It's on page 160, and you should read it. It's good to know. It's only a few lines. I just saw it, and I think it's very straightforward. And if you got questions about it, ask. But the one I do want to say something about is E. So I want to actually like prove E for you because it uses some good tricks that we've seen lately. All right. So for E, okay, this is one that actually is going to use induction, but it uses induction actually on the whole numbers. So I'm going to show that when it says for all non-negative integers R, that means like 0, 1, 2, blah, 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 which is the whole numbers. And I always struggled with how to write the Blackboard notation. I don't know how to do it. I usually just do that. I'm trying to draw the the fancy R. This is called Blackboard font. But basically I'm going to show this over the whole numbers instead of the natural numbers. So for a base case, you basically need to show that a to the 0 raised to the t equals a to the t raised to the 0. That you can kind of interchange those, okay? And maybe over here, actually, I'm going to do like a quick little aside. So a to the 0 is actually the identity matrix, and this one always kind of bugged me. So if you raise a matrix to the 0 power, it actually is the identity. And I want to show you because I think it's kind of weird to think about, but I mean, it's also pretty weird that like 2 to the 0 is 1, but when you see like how the properties of multiplication work, it actually totally makes sense. So a to the 0 times a to like some other power would be a to the 0 plus n, right? Which is just then a to the n. And so what I basically have here is something where it's like something times a to the n equals a to the n. And then that something would have to be the identity matrix. It's the only thing that works. There's nothing else in matrix algebra where you can multiply, something by itself and get itself. So really by like, what's the word I'm looking for? Basically convention of how these matrix multiplication works, you have that a to the 0 is the identity. That is true. If you raise a matrix to that power, you get the identity. So to show this with the base case, note that like a to the 0 transpose equals just the identity transpose, which is really just the identity, right? And anything to the 0 power is the identity, so that's it. And the identity is a symmetric matrix, so it's one of those where it's transposed as itself, okay? So this proves actually pretty quick once we jump into it now. So I'm going to assume that a to the k, that's a k, t equals a t to the k, and show that a to the k plus 1 t equals a t to the k plus 1. All right. So again, classic induction trick. Start with this. A k plus 1 would equal a times a to the k. And then I'm going to use the inductive step. So I want all this to be raised to the, not raised to the transpose, but I want the transpose there. Now, I'm just going to actually use D here, which I know I didn't formally prove, but it's in the book. If you have, I just wrote that wrong. This is the matrix in here, sorry. This is A to the K. So if you have a product, right, the transpose sort of does the socks and shoes reverse thing to it, okay? So I can peel off and write this as A K to the T, and then A to the T. And then this is where I'm going to use my inductive hypothesis. So I know AK transpose is A transpose to the kth power. And then I multiply that by A transpose. And then, if you just look at what we have, right, I have K powers of A transpose times another A transpose. And so this is really now K plus 1 powers of, whoops, I didn't give myself enough room there, the transpose. So it's AT to the K plus 1. And that does it. So it's just like a cool little induction problem that uses part D. And also, we haven't really talked about this, but if you raise something to 0 power, you really get the identity. So that actually holds for all the whole numbers. Again, just knock the first domino down, then assume somewhere in that chain it works, and show that kth one implies the k plus 1 case, and then just keep knocking down the dominoes, and it would show that all these work for all non-negative integers R.